Good morning and good afternoon. Welcome to today's webinar, IEC 61850 Tools and Techniques, Simulation of a Specification for a Digital Substation. My name is Beth Kapalis, and I'm the Marketing Manager here at Triangle Microworks. Before we get started, I'd like to go over some housekeeping items and some introductions. The webinar is scheduled to be 1 hour long. We will be stopping for questions a couple of times throughout the webinar, and we'll stay on afterwards to answer as many questions as possible. The audience is on mute, so please submit your questions online using the webinar tool under the section titled Questions. We have several folks answering questions online behind the scenes, and I will read and answer questions during the breaks and at the end. Next, I'd like to introduce our speakers. We have 3 presenters today. First, we have Thomas Sturks from ALIA Engineering. Thomas has been with ALIA for more than 7 years with a focus on IEC 61850 engineering and modeling. He is also a member of the IEC 61850 Working Group 10 and CGRE B568. Next, we have Christoph Brunner, President of IT for Power. Christoph is a well-known utility industry professional and 61850 expert with over 30 years of industry experience. Christoph has been involved in the development of the standard since the beginning. He is convener of Working Group 10 and member of Working Group 17, 18, and 19 of IEC TC 57. He is an IEEE fellow and a member of several IEEE working groups, as well as a member of the PSRC main committee and the subcommittee H. Lastly, we have our own Matt Green. Matt is a senior application engineer here at Triangle Microworks and has been with us for over 6 years. He specializes in QA testing with all our simulation tools in Gateway, works as a technical trainer on Triangle software tools, creates training videos, and participates in product demos for customers and conferences. So now that you know everybody, I'd like to give you a little bit of background on Triangle Microworks before we get started. Triangle was established in 1994, and we are headquartered in Raleigh, North Carolina. We have customers in over 70 countries and work mostly with equipment manufacturers, electric utilities, and system integrators. The products we offer all support the standard SCADA protocols and fall into 3 categories. First category is source code libraries. We license source code directly to manufacturers for use in their devices and systems. This allows for a much faster time to market and greatly reduces their costs and development time. We also provide testing tools supporting these libraries and protocols. These tools are used for communication testing in the lab or the field. They are designed to troubleshoot, simulate, and automate testing. Lastly, we also provide SCADA Data Gateway, which supports both Linux and Windows for protocol translation and data concentration with standard SCADA protocols, as well as OPC. We are heavily involved in the standards committees that support SCADA protocols, like UCA Group for 61850 and DMP user and technical committees. Through our participation, we help define the protocols, stay up to date on the changes that take place, and ultimately provide feedback based on our customers' needs as the protocols continue to evolve. So now that you know a little bit more about Triangle, I'd like to go ahead and hand it over to Thomas to kick off the topic we're here to learn more about. So Thomas, I'll go ahead and make you a presenter.
Yeah, thank you, Beth.
Okay, you should now have the screen.
Do you see my screen, Beth?
Yep, we can see it.
Okay, thank you. So good morning and good afternoon. My name is Thomas Sturks. I work for the Belgian TSO ALIA, and I will speak today about SCL specification from a user's perspective. Before we start, first of all, the agenda. So I'll introduce ALIA and the ALIA context, so you have a good idea of what our starting point is. Then I will specify what we call the definition of a good specification. Then a small part about how we specify or build our specification today. Then what we consider as what specification should become in the future. Then a little bit of explanation how the OSMOSE project contributes to that. And then I end with some next steps and the conclusions. So the ALIA is part of the ALIA group, which consists of two TSOs, one in Belgium, one in Germany, called 50 Hertz. And to start with the ALIA context, I'll first give some details about the technology that we use today and the way that we work within ALIA related to secondary systems. So what you see here on top is the current architecture that we apply in our current frame agreements for protection and control. So we are implementing Substation bus 61850 between the level of the bay and the gateway. Communication between protection and control cubicles per bay is still done in copper wiring, as well as the wiring between the protection and control cubicles and the field outside. What we are moving to in the future will be a full implementation of a digital substation, including substation bus and process bus. So let's start by saying that we use frame agreements for protection and control cubicles. These are frame agreements of 8 years that we have with 2 manufacturers. Our current frame agreement, which consists of this type of architecture, is called Specs 3. It's what you see here, and it's the ongoing frame until 2026. For the other general applications like busbar protection, RTO, DCS, etc., we have separate asynchronous frame agreements. We do our engineering maximally in-house, so our competences stay maximally in-house. We are focusing heavily on standardization and on templating. So for example, we have 52 bay typicals, which we apply in all of our projects. And we engineer and commission around 200 cubicles, protection and control cubicles each year. So what do we call a good specification? First of all, a specification should allow a correct interpretation. It should be complete, sufficient level of detail, and it should be centralized. So you don't have to look for an information in 5 or 6 different documents. No, everything should be centralized and should be complete and clear. Good specification also allows a correct evaluation of what you receive back from the manufacturer. So with clear criteria, measurable, and really easy to understand what the manufacturer is offering you. It should also allow a fast startup after your procurement stage. So you want to recover the effort that you put into your specification, so you don't have a long startup time and you can recover everything that you did before when starting your project or a frame agreement. It should also maximize testing possibilities already at specification stage. So you want to make sure that the specification that you build is of good quality. So and you want to verify that by testing it as much already as possible in the specification stage. It should also be reusable, so you don't have to redo everything for a next project or a next frame agreement. Very important also is that you are able to trace what you specified into the templates and the project files that are built afterwards upon that specification. And in that way also enable the automation of updates to all of these files when your specification is updated. And the last, but also very, very important one, is specification should not narrow down the market. It should keep open the market so you can get offers from as many manufacturers as possible. So now we've seen the definition of what we consider a good specification. This is a slide explaining how we specify and how many other utilities also specify their requirements today and how they implement them. Is by, in a first stage, creating specifications and requirements, which are mostly non-machine readable elements, just raw text, non-intelligent drawings, etc. With that, they go to the manufacturers and they have a selection and purchasing stage where they get an offer from the manufacturers and negotiate with them. But in most of the times, there's not a lot of time to go into real deep technical discussions with them in this stage. Then after the final definition, we start creating templates, which we then can use afterwards for executing the projects. And this is also a very effort-intensive stage because until now we could not recover anything from the earlier stages. We cannot recover the effort that we already put into our specification into the creation of the template. So this is everything needs to be started up from scratch, very effort-intensive. And again, we have a very limited time because the need of the projects is behind it. And so we need to move forward very fast. It's also the first time that we can provide feedback to our specification because it's the first time that it's really been used for projects. So this means that we have to wait until the creation of templates before we can really verify if our specification was well built. And then again, if we detect errors, it means that all the templates that are affected need to be modified manually because we did not recover any effort. So indeed, the last point about feedback I already covered. And when we compare the current process then to our definition of a good specification, we see that on almost each of the points, almost all of the points, our current process does not respect the definition of a good specification. So we identify here that this is not the best way to work. So what we did is we tried to enhance the process in order to be more in line with the definition of a good specification. And what we identified is that we need to extend the part that is before the selection and the purchasing. And we do that on different levels. So we want, first of all, more the ability to prepare and test things in advance. Because we want to have the ability to provide feedback to the specification in a stage where we did not yet select or purchase anything. So we can go to the manufacturers with a specification which is of a high quality. And in order to do that, we also want to include more automation and efficiency by making things more automated, not only for the user in the creation of the specification, but also for the manufacturer, which needs to respond to your specification. And in this way, by preparing more in advance and allowing more automation, speeding up the phases after the start of the project. Because we prepare more in advance, we can create our templates easier and more efficient, so we can start with projects in an earlier stage. And what you see here is the updated process, where you can see that there is now, in the earlier stages, already more feedback possible to the specification. And how do we do that? By creating vendor-independent templates, which are machine readable for the vendor, and so that we can move forward in a more automated process. How does the OSMOSE project contribute to this? So first, a small introduction of this project. So OSMOSE is a research project which is sponsored by the European Community. And a part of this project is dedicated to the enhancement of the 650 engineering process. And the result of this research has provided ways to now specify system data flow inside SCL without having to allocate anything to an IED. So we can now really specify in SCL the way we want our system to behave, the way data needs to flow between elements without having to introduce IED elements or vendor dependent elements into it. So we can really make an independent specification. And also we can now trace the specification into the files that that reflect the implementation of the specification. So these are two very important points which allow us to respond more to our definition of good specification. And how do we implement these 2 points? By extending the SCL language with additional elements, which allow us then to remove the layer of the IED and the vendor-dependent layers of the SCL file in order to get a vendor-independent file. We did that in close collaboration with the 6150 standard, more specific the 6100 part, to guarantee that all of the things that we are identifying and developing within OSMOSE get introduced into the standard. So the 6100 will implement the recommendations and the developments that we provide within OSMOSE. We also demonstrated our developments. We demonstrated the extensions within the OSMOSE project with tool and product prototypes from different vendors. Now, what is the impact of all of this on tools? First of all, specification tools now allow to create a vendor and IED independent system specification. There is a new need for tools identified, what we call comparison tools, which allow to compare what you specified with what you get back from a manufacturer. And for example, also allow to compare what you specified with the final implementation with the IEDs of the manufacturer. So this is a new role for tools that we identify and which can help the user during the engineering process. Configuration tools can now use also the data flow that we include in our specification to implement it in an automated way. So if we already provide specification with included data flow, a configuration tool can now use this specification to automate the data flow between real IEDs. For testing tools, we also see new possibilities in, for example, now testing a specification which does not yet contain any IED or vendor information, allowing a user to verify the quality of his specification already in a very early stage. But the work is not finalized, so we identified a lot of things within OSMOSE, but we are still identifying other things that are still missing in order to really get to a good and a final specification which is conform all our points of the definition. For example, we want to be able to specify also physical interfaces of IEDs so that we can have the ability to specify if we want a signal on a binary input of an IED, for example, without having to specify the IED itself. Or, for example, wanting an analog value on an analog input of an IED. So we really want to be able to model the IED already in specification without having to include real IED or vendor information. We also want to be able to define application templates. So we don't have to repeat many times the same actions in creation of the specification. So we want to create at specification side templates which we can then reuse during the next steps in the process. We also would like to introduce functional variants, for example, so that you can quickly, with some easy selections, modify your specification in order to make it correspond to specific specification cases. For example, your specification is slightly different depending on the voltage level that you work on. With functional variance, you could easily then adapt in an automated way your specification to the specificities of that voltage level. And as a last point, we also want the possibility to link what we call the description of a logical behavior of your specification and link that to the SCL file directly in order to get a more centralized specification and have all data in one place. And so these are only some examples of the things that we think are still missing in order to really get the best possible specification. But as I've shown here, OSMOSE is already providing many improvements. So this was my last slide. Thank you for listening, and that's my presentation.
Great, thanks, Thomas. Now we're going to switch over to Christoph Brunner. So I'll go ahead and make you presenter, Christoph, and you should now have the screen.
Yes, thank you, Beth. Just need to select the screen that I want to show. You should see my screen now. Yeah.
We can see it.
Okay. Good morning as well to everybody from my side. What I want to present now in the next presentation is a little bit the concept of an application in the context of IEC 61850 and the way how we can specify that from an IEC 61850 perspective. So what we see on this slide is that applications, when we look at applications in general, they are built by exchanging signals between different functional elements. That's how we typically create an application. In 61850, the functional elements are logical nodes, and the information exchange between these logical nodes that can be internal in a device if they are implemented in the same device, but it can also be external, and that's when we typically use GUIs if the logical nodes are in different devices. So what we see here is such an example of a logical node that has outputs, which are the data objects, data attributes standardized in the standard. These outputs may go as signals to other logical nodes, to other functional elements. We also get inputs. Inputs today are not standardized, but we can at least describe where we get an input from. And we also may have parameters and controls as elements of these logical nodes. The next slide here gives us an example of an application in IEC 61850. And the application is basically breaker failure. So we have somewhere our protection elements. In this example, I show a few distance elements. The signals from these protection elements go to a logical node that is the trip logic, the logical node PTRC. From there, the trip, if we need to trip, is going to the logical node XCBR, which is the interface to the switchgear. And we may have a physical wire going out of the device to the opening coil of the breaker. But at the same time, this trip signal will initiate the breaker failure function, which is the logical node RBRF. The breaker failure function will supervise that the breaker opened. If the breaker didn't open, it can either do a retrip, and if it's still not successful, it has to clear the surrounding breakers, which is done with the standardized data object operate external that is sent to all the other XCBRs of the concerned breakers that may need to open. So that's basically the application, how the different signals between the different logical nodes work together to implement such an application. Now we can allocate that to devices. And in this case, we have a first device here, the ID1, which would be the protection device. In our example, we implement the breaker failure function in the control device, so that will be a different device. And then, of course, we have the additional IDs in the other base that would interface to the neighbor breakers that we need to clear in the case of a fault. What we see now is we still have internal signal exchanges between these logical nodes like before, but some of our signal exchanges are now going between the devices, and that's where we typically will apply goose messaging. In the traditional world, you would have applied wires there, you would have routed this signal to a physical output, you would have created a wire going to a physical input in the other device. With IEC 61850, we now can use goose messages there, so we basically have virtual wires, virtual signals, virtual connections, but now we are using goose messages between the devices to distribute that information. But in principle, the concept of the application stays exactly the same, whether there is devices there or not. What we can already do today in 61850, we can describe when we have a goose message between the devices, we can describe through the use of XREFs where signals are getting into a logical node. As an example, the logical node from a neighbor breaker that would need to trip when the external signal gets activated would have, among other, an XREF, which basically represents an input, an XREF pointing to a signal op-X that he has to subscribe somewhere from another device, from another logical node, RBRF in another device. That's what he can already do today with 61850 edition, the part 6 as we have it today. Now, when we look in general how we have to implement an application in IEC 61850, we have basically 3 steps. We start, like Thomas explained, with the specification of the application, the details of the application, which means the signals that have to be exchanged between the functions. This corresponds to a wire diagram that we had in a conventional design. We then will allocate functions to devices, and at the end, we have to translate the signals that need to be exchanged between the functions of the devices into goose messages. With IEC 61850 part 6, as it is today, this can only be described at design when the IDs are added. And that's why what Thomas already mentioned, we wanted to get a step further. And in this part 6-100 that we are working on, we define a couple of extensions. Among them is also the extension that we already can specify interactions between logical nodes in the specification stage. So when we do not yet have IDs associated to our system. And that has been done by adding a new element source reference as inputs to L nodes. The L nodes are the ones that we have in the substation or process section. This is comparable to the XREF that are inputs to the LNs in the ID section. But with that, when we create the specification, we can already define the details of our protection schemes. Like Thomas mentioned, he would have the possibility in the future to do that. And as he mentioned as well, this allows to test the scheme already at the specification phase using simulation, and that's what we will see later on in the demonstration. Now, let's get to the step of verifying the concepts. As Thomas had mentioned, the OSMOSE project has worked together with the working group 10 of TC57 to define those extensions to the part 6 in the 6100. And we have established a demonstrator where 6100 extensions are tested with tool and products prototyping those extensions. The demonstrator is emulates in principle 2 substations at 2 ends of a power line. It implements the 2 feeder bays in the 2 substations. Functionality includes protection and control, including reclosing and a permissive teleprotection scheme. We have real IDs that are connected to a real-time simulator that simulates the power system. The demonstrator is set up in the laboratories from R&D Nestor in Lisbon. Tools are supporting the extension from 61850-6-100 are used to test the whole engineering process, as Thomas has mentioned that. One of the applications that we now will later on demonstrate how we can simulate that is a teleprotection example. So this slide is the teleprotection example from the OSMOSE demonstrator. So we basically have 2 protection zones. Zone 1 protection, which is the protection up to maybe like 75% of the line, which will do an immediate trip. But then we have the second zone, the teleprotection zone, that is overreaching. So that's to cover the areas of the line that are far away from the own substation. But as the zone goes beyond the other substation, we need to get the permissive signal from the other side to make sure that if the fault is between the two substations, so that we don't trip when the fault is beyond the substation. So that's why we have to exchange also teleprotection signals. So if we have a fault, if the substation on the left side sees the fault somewhere here, it will see the fault only in the teleprotection zone, and the teleprotection zone will only trip when it gets the permissive signal from the other side, which is sent when the other side sees the fault as well on the line. Then we will get the permissive signal and will trip as well. If the fault is beyond the substation, this substation will not see the fault on the line, it will not send a permissive signal, and we will not trip. And that's an example that now will be demonstrated in the next part by Matt, simulated in DTM based on the SCL files that we have created as part of the OSMOSE project, and that includes this 6-100 enhancement. And with that, I hand over back to Bess, respectively to Matt.
Great, thanks, Christoph. Yep, Matt, I'm going to make you presenter. And while Matt just gets his screen set up, I just want to remind everyone that you can feel free to submit any questions that you have online, even while the presentation is going on. We do have several folks sitting behind the scenes ready to answer questions, so it's just a great time to kind of ask the expert. So with that, Matt, I'll go ahead and hand it over to you.
Thanks, Beth. So now that Christoph has gone over this in PowerPoint, let's take a look at an example. We're going to look at the OSMOS sample application, specifically at two protection schemes triggered by different fault conditions. The OSMOS sample application defines two different substations, SSA and SSB, that communicate via teleprotection. The first fault we'll be looking at today is noticed by both SSA and SSB in Zone 1. The second fault will be outside of SSA's Zone 1 and will rely on SSB's teleprotection. We will be looking at these protection schemes and how they're handled within the SCL and how they can be simulated in DTM. So on my screen right now is part of the full signal flow diagram for how these protection schemes work. But for the first fault, we'll be looking at this section here. This is the signal flow for the three-phase distance protection scheme to trigger a trip on phase A, B, and C breakers when a fault is detected within Zone 1. So let's take a look at this inside of the SCL file. As defined in the 61850 engineering process, substation design tools will generate a system configuration description file, or an SCD file. This file contains the substation architecture and all of the IEDs required to implement the system. The OSMOSE project enhanced the specification step within the IEC 61850 engineering process. The specification step generates a system specification description file, or SSD, whereas the design step is when the SCD file is generated. The SSD contains a substation section, like here, and the substation section defines the architecture of the substation. It can also optionally contain the definition of virtual IEDs. Virtual IEDs are start to splitting up the functionality of the substation into IEDs, but they don't necessarily correspond to any actual IEDs yet. The OSMOSE project relies on the fields labeled with 61850-6-100, and you will see these fields in the SCL files in Navigator. So the OSMOSE project's sample SSD file for Substation A contains the complete definition of Substation A and a minimal definition of Substation B. The only parts from Substation B that are necessary for the functionality of Substation A are included in the SSD file for Substation A, and this goes vice versa as well. So for example, we have the entire SSA description here, but if we drill down into the SSB, you'll see we only have the function definitions for the teleprotections. In 61850, a substation is defined by one or more voltage levels, and then inside the voltage levels, you have one or more bays. Inside the bays, you have conducting equipment and a set of functions. Conducting equipment is like breakers, switches, current transformers, things along those lines, whereas the functions are a list of signals and logic required to run the functionality of your substation. So if I open up one of the conducting equipment here, you'll see terminals. And these terminals are defining the connectivity of the lines in your power system. And if I open up one of the functions, say this trip logic here, we'll see that we have all of the logic and signals required to implement all the functionality for this specific function. For example, in this trip logic, we'll see that we can drill down into the three-phase power, and we'll see that there is a PTRC here. And there would be a PTRC for both the single phase and the three-phase protection, but we're going to look at the three-phase right now. In 61850, a PTRC logical node monitors all the possible sources of trips as inputs, and then determines if the trip signal should be sent. And if it should be sent, it'll go ahead and generate that trip signal and send it. The OSMOSE project uses the IEC 61850-6-100 namespace that augments the 61850 specification to allow for a more complete definition of your system. So the first thing we'll look at here is just this power system resource. This power system resource element associates which piece of conducting equipment that the function we're looking at applies to. The next thing we're going to be looking at is this PTRC. The default behavior for the PTRC is defined in DTM, but the inputs to this behavior is defined by the 61850-6-100 source ref elements. So I can open that up and show off all the source refs here. So for example, one of the inputs that could potentially be a trip is defined on this line here. And you can see the input is defined here. And you can also see where the source of that is coming from within the SSD file. So it's a distance protection scheme, and it's op general. So now let's take a look at what that looks like in DTM. When DTM imports an SSD file, it creates a substation structure like we just looked at in Navigator. So we can take a look at the SSA, that's the substation. We've got our voltage level. We got our bays, and now we have our conducting equipment and our functions. If we look in one of the conducting equipments, you can see that the terminals defined in the SCL are also shown here, which helps us define the power flow of our system and also helped us hook up a single line diagram to show off the substation. We can also navigate down to that trip function we were looking at, open up the three-phase, and look at the PTRC logical node we were talking about before. And if I open this up here, since I already pointed it out, we'll see that one of the inputs, this operation general, is in fact coming from that protection, distance protection, and op general. Since everything has been properly linked in the SSD file, I can actually go ahead and just immediately start interacting with my simulation and verify its responses. It's worth noting that we're not simulating the reclosing or the busbar protection functionality to better demonstrate this distance protection functionality, but all of those protection schemes would be handled in the same way that we are showing off today for the distance protection. So I can create a three-phase distance protection fault on zone 1 by clicking here and verify that both of these breakers have been opened. This is because both substations see in their zone 1 the fault, and anytime a zone 1 fault is detected, the breaker should open. So let me reset this and run a different test. If I generate a fault here, which is outside of SSA zone 1, we'll see that they both still open as well. And this is because anytime a fault is detected in the teleprotection or TPR zone, and you receive a TPR permission signal from the other substation, the breaker will still open. So in SSB, the breaker opened because this fault is within its zone 1, like previously. But over here, we have both the TPR section where the fault was being detected and the permission signal being sent over from SSB here had this breaker open as well. So let me reset it one more time. The last test I'm going to run here is specifically for distance protection for SSA on a bus fault. So if I click this, we'll see that neither of the breakers opened. SSB still sees the fault in its TPR zone, but it does not receive the TPR permission from SSA, so the breaker remains closed for that reason. And on the other hand, SSA does not see the fault in its TPR zone because it's behind it, and the breaker will remain closed even though it did receive the permission from SSB. So let's take a look at this teleprotection functionality in a fully formed SCD file and see how DTM will handle this. So just for time's sake, I'm going to go ahead and load up the workspace that has the SCD file, and then we can jump back over to Navigator. So this is our SCD file in this other tab. So similar to the SSD file, similar to the SSD file, you can see we still have the substation sections for SSA and SSB, but now we've added all the IEDs to add a more complete design. Just like for the SSD file, for substation A required a minimum data from substation B to define its functionality, the SCD file requires a minimal amount of IED data from substation B to support the teleprotections between the substation. So let's take a look at the teleprotection fault, and let's see how that's defined in the SCD file. So following the same process, we can open up the substation. We can go down to the voltage level, the bay. We've got our conducting equipment and our functionality, but this time I'm going to go to teleprotection. And so what we'll see here is we still have the source refs like we did in the SSD file, and we still have what the input is named and the source it would be coming from. But what we've added in the file now is the XREF address. This XREF address is the input to the logical node from an actual goose signal from an IED, and it replaces the source when it is used as if the source was used in the SSD. Now we're in the SCD, so we're using the XREF address instead. So let's go back over to DTM and take a look at some of the new areas we've added. The first thing we've added is obviously the IEDs to the substation. And because we have these IEDs, which are doing reporting and goosing and everything that you'd expect from a 61850 server, I can even open up this model here and see all of the logical devices, the logical nodes, data objects, data attributes, everything like that. We also at the bottom here have a goose tracker. So when any goose message is sent, we'll be able to see that happening in real time as well. So I'm going to go ahead and activate that zone 1 fault again here. And what you might see if you're paying attention is that the start general does go true for a second. But even if you miss that, we'll see that the time has updated, verifying that the 61850 IEDs are having their database updated. And we should also see some goose messages being sent out as well. So if I click this, again, you'll see these breakers open because the fault was in both SSA and SSB zone 1. We'll see that the time period here has updated. And then if I grab a little bit more area down here, you can actually interact with some of these goose messages and see what values are being sent across the line as the goose messages are being sent out. So that is the full live demo that I was going to give with our 2 applications here, SCL Navigator and a Distributed Test Manager, or DTM. I will be handing it back over to Christoph now to discuss what if you don't need the default behavior, but you need to customize the logical node behavior using 61131.
Okay, thanks, Matt. As I hand it over to Christoph, we did have a couple of questions that came in, so I'm going to pause and just take 1 or 2 questions because we are running a little bit close on time. So the first question is, I think, directed for you, Matt. What was the tool that you used to look at the SCL file?
Oh yeah, absolutely. So this is our SCL Navigator. It is a tool that you can use to build and edit and verify all forms of SCL file for 61850. It's got a ton of functionality. It's really been designed from the bottom up to support 61850. Correct me if I'm wrong, you can just go to our website and download a trial of it and give it a shot and see how things load up like that.
Yep. Great, thanks, Matt. We have another question that came in. I think this is directed to you, Christoph. Are you going to use LGOS? And if so, can you elaborate?
This demo does not use LGOS in this context. LGOS, if it would be used, would basically indicate that a device that is supposed to subscribe to the message actually received the message. We have demonstrated the use of LGOS extensively in a previous webinar, and I think that webinar is still online so that you can download and see how we would test and how we would use LGOS in a real application.
And just to throw a little bit of more information there, the webinar he's talking about, it's still out there. You absolutely can still go watch that. You can actually follow along with it if you download the applications we use in the webinar, because we have built in the workspaces that we use for that webinar straight into our samples. So you can download them and follow along, right along with us in the webinar and see how LGOS can be used within the simulation tool and our debugging tool.
Great, thanks. I think I can take one more question before we'll switch back over to Christoph. Does the wire diagram also show network switches present in the 61850 topology? I was interested in evaluating different network topologies and routing algorithms. I'll open that up to anyone on the panel.
So if that was directed toward DTM, we just kind of have a single line diagram here for the electrical equipment. This doesn't necessarily show off any routers or switches or things along those lines. If that's not directed toward DTM, I will be happy to let someone else continue to answer this question.
Yeah, I'll jump in real quick. Just so the single line in this demo was developed using our Insight display capability, which is really a generic drawing tool. So the reality is, yes, if you wanted to overlay communications and network communications or topology on this diagram, it would be fairly easy to do. It's a generic drawing tool. We just, in this case, used to draw the single line.
Yeah, that just maybe add on with 61850, basically we have the possibility as well to describe, include network switches in the communication and describe the connectivity of that in 61850. So that's basically using the extensions from the part 90-4, where we have model of switches as well. So this supports as well the possibility to describe a network diagram in details.
Great.
And I did just bring it up a little bit. This is how you would build up a display. So we built up a single line diagram using some of these tools here, some of these items here, but we have tons of little palettes where you can come in and add in processes and valves and pipes and counters, and all of these kind of symbols can be used generically or overlaid. So yes, I appreciate you chiming in there, Dave, and following up on that, because these displays can be made however you want them to be.
Great, thanks for the detailed answer. And just for everyone in the audience, that was Dave Galkenauer from Triangle Microworks. He's our lead DTM developer and part of the panel of experts, folks answering questions behind the scenes. So with that, Christoph, I'm going to go ahead and make you presenter again so that you can continue on with your demo.
Okay, so you should see my screen again. So in that last part of the webinar, I will show how a feature that will be included in the next version of DTM can be used to prototype an application. As Matt has mentioned, it's basically adding the capability of using 61131 to specify behavior and simulate that behavior to DTM. which is basically in line what Thomas has mentioned, that he wants in the future as well to be able to include logic behavior description in a specification, so that we can even easier simulate the specification. The example I'm using is again from the OSMOSE project, an additional part of the OSMOSE project. The OSMOSE project as such deals a lot with storage system. An additional part where we had worked on was also related to verify the concepts of 61850-7420, which is a part of 61850 dealing with models for distributed energy resources. And the little use case that we have invented for that purpose is the usage of a storage system to basically prevent an overload of the line. So what we see here, we have our two substations that Matt has shown before that we simulate. We have the power line between them, and we assume now in a first step a power flow going from the one substation to the other substation. So this will be the collective sum of all the other feeders except the ones to this power line, and the same this on the other substation. That would be a summary load out of that substation, and the energy has to flow over this power line. In order to prevent an overload that may happen in certain situations, we now introduce on both sides a battery system as a storage. And the idea is when the power flow here goes above the threshold that we have from the line ratings, the battery down here would take the lead, would feed in this excess energy out of the battery instead of pulling it here from the line. And to compensate, on the other side, the battery would store this excess energy that cannot be pulled over the line into the battery. So with that, the power flow, the overall power flow remains the same, but we have a kind of a virtual power flow between the batteries. The battery on the load side will drive that with a function called load following, which is described in 61850 as well. It's a standard function that exists in the DR world. So it would drive that, and it would tell the other battery what it has to store to compensate what this battery would generate. Now, the first thing we wanted to do, we wanted to verify that as models in 61850, and 61850 part 7420 basically has a high-level abstract models for DRs. We talk about operational functions that basically implement the grid codes, and in our example, the load following function, that would be one of the operational functions. We then have a power management. That's the function that is doing the complete algorithm, so that will decide what the battery has to do. And the interface battery would be to the group of what we call DR resource logical nodes, which could be generators, load, or storages. Just to quickly say that the load following function, so that's basically what we need. If the load goes beyond a certain threshold, instead of pulling it from the line, the amount we pull from the line will be constant, but the additional energy, the additional power that we need will be produced by the generation following exactly up the demand of the load that we have. Now in 61850, the model looks like the following. We have on one side our operational functions, so that would be the logical node modeling this load following function. We also use active power generation. That's what the other side would do when it gets the request from the other side to act as a load. So this basically requests generated energy. This would request to store energy. In the middle, we have our power management function. That's where we implement the whole algorithm. So that's where we decide when we have our requests that we should follow up load that we need to generate. We will have a output that goes to the generator. So here we have the DR resources. We have an output that requests to generate energy, which goes to the battery. In the case we would get the request from the other substation to store energy, the power management function would analyze that and probably request to charge the battery, but it also supervises from the storage element the state of charge, I mean, if we are too low, we cannot generate anymore. So that is also supervised here so that we don't generate requests that we cannot fulfill. So that's basically the application that we had in mind. And now we will see how we can simulate that in DTM using this new feature of the 1131 language. What we see now here on the display is another workspace of DTM, where we now have defined an application, an 1131 application. We can do that with functional block diagrams. That's the functional block diagram that you have seen before in my slide, that basically models that complete application of this DR controller, of this battery system management system, basically. So this has been described in function block diagram, and each of these logical nodes, its own, is described in structured text. So we can program the behavior of the logical node, in this case, the load following. We can program that in structured text, and then we can run the application. We also created a second application, which is basically the simulation of the battery, as we are not connected in this case to a real battery and to a real power system. We also simulate the battery behavior. So we have a known program running in this 1131 environment that simulates the battery. And now we can see how that works out. What we see here, we can watch certain variables. I have added the variables like the load that we have to follow, which is currently 0, request from the other substation. I may go back to the diagram so that you see these signals. So that's basically the load that we supervise. If that goes beyond the threshold, then we will have to generate energy from the battery. And that's a request from the other substation that would request that we have store energy in the battery. And these are the outputs from the complete function, but the request, what we have to generate, what we have to charge, a request that we would send to the other substation. We see here the state of charge. The initial state of charge of the battery is 50%, which represents 100 watt hours, 100 kilowatt hour, or whatever, that we have from the battery simulation. And we can now change some of our variables. So we see the threshold is set to minus 1500. The rating of the battery is 200. So the state of charge of 50 is 100. And now I can simulate a load that we have to follow. If I say our load is minus 1000, we still should not generate anything because we are still in the range of the threshold, which is minus 1500. If I increase that to minus 1600, we now see we got a request to generate 100 watt or kilowatt, and on the same time we sent the request over to the other substation to store this amount of energy. And what we see here now, that we are generating this amount, the battery state of charge is going down as we are consuming energy out of the battery. On the other system, the state of charge would go up in the same way. Now, if we go back, now we are again in a normal condition. Let's assume we go back to minus 100 here as load. Now we are back in a normal condition. You see, we are not requesting anything anymore. The battery stays where it was. And now let's assume that the other system, the other side requires us to store energy in the battery. I can set the value here like minus 200. And now we see we have now a request from the other substation, and we are supposed to charge with 200. And we see the state of charge in the battery is going up again, and the energy as well in the battery is going up. And just to make it a little bit higher, to speed up, we can also charge more. So now it's still charging faster, but so it's still charging. So with that, we can simulate the behavior and we can verify that the concepts work in this environment. And with that, I'm at the end of the demonstration, and I hand back to Beth for the final questions.
Mhm. Thanks, Christoph. That was actually perfect timing. So with that, we have filled our hour. We have ended it perfectly at 1 hour. So I do want to wrap up with some final thoughts. The webinar that you've seen here today is being recorded and will be posted on our website at trianglemicroworks.com. You'll be able to find it there in a couple of days, right on our homepage. Just scroll down to the bottom. It will also be on our YouTube channel, which has tens of other videos of our past webinars and training videos on the protocols and our tools as well. You can download evaluation licenses, as Matt had mentioned earlier, of any of our tools. The ones you saw here today were SCL Navigator and Distributed Test Manager. So feel free to try those out. And certainly I welcome any questions or comments. Please email me directly at bcapellis@trianglemicroworks.com. When you do log off of the webinar, you will receive a short survey. It's only 4 questions, but we appreciate if you take a minute just to answer those and give us any feedback you have and any additional topics that you'd like to see in the future for a future webinar that we're happy to host. So again, I thank everyone for their time and look forward to seeing you on the next webinar. Thanks, everyone.